Hi everyone, thanks for being here. It's actually great to have a quantum session in such a high quality conference. So today we'll present you AccelerQ. That is our attempt to optimize quantum eigensolver with machine learning. And don't worry, I'll give you all the information you need about eigensolver to follow the talk. So first of all, why do we need to optimize quantum software? So in a general use case, we used to have software engineers that built software, hopefully with some good practice about software. And it's for a specific audience, but here when we're talking about quantum software, it needs a lot of expertise on quantum physics actually to follow some basic quantum physics properties. So it's usually quantum experts that build those software, and they are aimed for quantum experts at the beginning, but now we have also a use case for medicine or financial use cases. So it's because of this very multidisciplinary aspect of quantum software that we gathered a multidisciplinary team in King's Quantum to try and see if our gather of knowledge can actually help optimizing those software. And we picked a very specific problem that is quantum eigensolver. And the only thing that you need to know about quantum eigensolvers for this talk is that it is search iterative process, and the aim is to find a specific property of a quantum system. Usually it's the minimal energy of a molecule, for example. And it's very hard to do. So you have to make an educated guess and go over it several times until you reach the desired output. And the most prominent quantum eigensolver that is out there right now is called a variational quantum eigensolver, and it's one of the examples that we go through the paper. If you want more details, we have very accessible definition of all this notion in the paper. But the principle is that you have noisy quantum hardware in the middle of a classical optimization loop, and you have to tweak some parameters and go over the quantum computation several times to actually find the results you want. But the problem is that those parameters need a lot of expertise actually to understand how they affect the computation. And so if we want to optimize it and to plug it into a machine learning loop, we want to abstract out those problems. So the first thing that we did for for this work is to basically take these algorithms and this instance of algorithm and put them into a box and go over all the parameters that can happen in this, that we have to tweak in this optimization. So that's the one example of such a parameter. And I guess you don't understand what it means, but maybe this guy does. And so when you talked with experts and you asked them if they ever switch to something different than the default parameter for many of these parameters, most of the time they say no. But when you work with them, you can actually define some boundaries and some structure of these notions. So that's what we did. And we basically created first layer of abstraction. And I'll let Karine explain you what we managed to do with this layer of abstraction.
Yeah. So we're going to treat everything from now on that we give to the simulator as a code. And to understand, first of all, how this code is working, because it's very complex, we don't have a lot of understanding. What we did at first, very classically, no quantum computer involved, we start doing some data preparation. So instead of trying to do some very specific analysis or static analysis of the code, what we did, we took very small system and start sampling them with the implementation, with the code that we have. We sample them many times and create a set of data from very small samples, so we took some small system, we create some data array systems. I think I will just look at the screen. And then we classically, because this is a very small system, we can just compute it mathematically based on the specific code that we have, because it implements something very specific. We compute the result, like the property we want to learn or to know from this system, and then we train some regressor, and then that's the part when the classical stuff ends. And then using this small train model that was trained on small system, we move to bigger system and we move it to the quantum computing. And then with this, we select different better relations. So these constants are not always just constant like 5, but they sometimes represent some relations. So if I put 5 here, then somewhere else maybe I need to put 200. And if I put 4, maybe then this 200 is no longer valid. I need to put a different number. So they have a bit more complex relationships there. And then we run we use this we deploy this model and find a better value for a specific large quantum system with this specific implementation with the code I have in my hand. So the code gets some quantum system and does something on it. Yeah. So and the code is just like Python code with a bit of libraries. And then we find the better numbers, and then we plug this number back into this implementation with the system we care about, and then we run it on a quantum computer, and hopefully we get better results. The problem is that this part is too greedy. So what usually machine learning does when it learns some function, it becomes very greedy. It will try to take maximum resources. It try to do a lot of things that doesn't make a lot of sense. And to understand it, you have to a little bit dive into the parameters there. So, for instance, this is some of the numbers and the meaning and the relationship that might involve that we took from when we analyze each of the code. So, for one of the implementations, we took 2 implementations. One called adapt QSCI, and the other one called QCells. They're both algorithm that solve the VQE problem. And we took 2 different implementations written by different people. And I just look at one of them because we don't have enough time, I think, to dive to all of it. So some of it's like num pickup, for instance, is how many, what is the level of abstraction? So how many elements inside my quantum system I'm actually pulling and giving to my code, to my implementation. Cutoff is the same. It's like if some elements are too small, when I can start ignoring them. So it's also part of the abstraction of the quantum problem, and so on. So all of these are very somehow control how much information I am taking out of my quantum problem and giving to the implementation to work on. Two very interesting things is the number of sampling shots. So we cannot sample as much as we can, and we cannot we cannot sample a million times, and we cannot run infinite amount of stuff in the computer. But what usually do when it's too greedy, they're trying to raise all these numbers. So they want to get maximum precision, a lot of very longer time, so you can get better assurance of your number. So this is a pro. Yeah. So this being too greedy, in that case, will give you very, very high accuracy, and you have a lot of freedom of what of the settings and the assumption on the quantum problem that you allow your algorithm or your code to know. Of course, the cons is that it's going to run very, very long time, and the gain might not be at some point we get to a plateau. But in reality, unfortunately, the hardware will terminate much earlier because we have quantum noise, and so once you go to the hardware, you have a very limited time when you can, very, very limited time so you can do the cycles and you can do the sampling. You cannot sample forever. You cannot run this software forever. That's because of how, in general, you can never run forever, but in quantum is much more aggressive. So we cannot run, so a good thing that we don't have extreme runtime because the hardware will stop much earlier, but we also lose the maximum accuracy. And to be honest, what happened in the end is we just we waste all our time at the beginning of the problem and not at the end of the optimization problem, and then we get very low accuracy. So what we did, we defined a set of relationships. So I know that I can have 200 iterations, but then each iteration I only have, I don't know, 200 shots. But then if I move it to 20 iterations, then I can have much more iteration during, much more shots during the iterations. And there are actually much more relationships, but and you probably need to go to the paper to understand these. I think just the number of shots and the iteration are the easiest to explain. So what we did to solve this greediness, we write a sequence of tests that either just look at what I told you, the number of iterations versus the number of shots during each iteration, and see that we are not sampling, we don't have too many shots in total, but there's other properties. So one of the things is self-selection, is when you can reuse some operator again, and there is the final, when we decide like things related to the stopping condition, and we wrote tests. Some of the tests requires running some sample of the code of our implementation, of the VQE implementation, to see if the numbers make sense. Some of them you just can compute it statically. And what we did when we run the test, so the default is the default parameter. With the optimization, let's say it can have, let's say, 0 and 1. And then if I do the test, then the test actually said, no, 1 is never possible. It doesn't make any sense. And then we remove this value to avoid this greediness that leads us to suboptimal solutions. G is about the stopping condition. So with the test, you see that it can select much more broad number of values. And with the test, you can see that the bottom values, the lower values are just chopped away because they're no longer making sense with this specific implementation. So these are some of the tests we wrote. So you can imagine that some of them will be, so the static one is here, which usually you can just check with this one. This is the number of iteration versus number of shots per iteration. And some of them are require running some code and observing the result, like a small part of, not the whole algorithm, a small part of it, and observing the results. So we run this, and there's half of the paper I think is evaluation, but just a little bit of the results that we got. If you look, the black line is, we can look at one of the algorithms. So the one with the black line is the default parameters, and let's say with the pink and the green one is, the pink is with the test, and with the green is with the, the pink is with the optimization only, and the green is the optimization with the tests. And you can see that, I don't know and you want, obviously, the value to be, so you want to look for the minimum value, yeah? So you can see that the green sometimes, and sometimes the pink are actually the one who's taking. The other implementation sometimes might have a better result, but if you just look at the adapt one, then you can see that the black here is up, and the green is sometimes below, and sometimes the one with just optimization wins, and we have similar results here. Here is a bit more noisy. This is the size of the system of 20, 28, and 24 and 28. Yeah, and that's all. I think the conclusion you can read, and when I prefer to leave it for questions now. Thank you.
Questions, anyone? We have a microphone. How long does this process take? Going through and picking the right hyperparameter for the biggest case of 28 qubits.
I think that this is not very, it is quite quick, like you can do it in an hour or two.
An hour or two?
But the evaluation to get these numbers, this takes months.
That takes a while.
That took 3 months for each system.
Running on a simulator or on a
computer? Simulator, yeah.
Okay, 3 months.
Yeah.
Very good. All right, thank you.
Thank you.